All right, ladies and gentlemen, I just want to get a quick little video in here to sort of go through the whole unit here, Unit 4, our work, energy, and power unit, just to sort of lay everything out there. And at this beginning portion, I'm kind of going to go through the same notes we went through today in class, but I'm going to talk through them a little bit more so you can pick out some of those finer points. Next to me, I also do have a copy of the test. So I will be making sure to hit some of the main questions there without actually giving you them, but just giving you some direction on sort of where to go with your studies over these next couple of days. So first thing here is just some of our basic equations that we started out with, and then in a little bit I'm going to connect a lot of them together. And someone today said, it's not that necessarily this is a hard unit, it's just there's a lot of stuff that's interconnected with each other. We've got work that equals a change in energy, but if it's net work, then it's just a change in kinetic energy. And all these sort of going together in different ways. So we're hopefully going to try to sort some of that out here now. So to start off with, we're going to basically start where we started at the beginning of the unit. Work is force times distance times the cosine of theta. So if we have any problem that is talking about force as opposed to speed, this is where your mind should kind of go, to these two equations, one of these two. If you're talking about force, that's really the only place we saw force at. So if the question mentions force, I would be thinking of work as F delta x cosine of theta. There are other ways for us to calculate work, but in the cases where we have force, this is likely going to be your best bet. So whenever we have a force that is applied over a distance, let's say I had a box and I pushed it to the right with a 20 Newton force, and I pushed it for 5 meters. As long as I have a force across a distance, I have some work done by that individual force. Then we can also expand that out a little bit to include not only just a single force, but a net force. Same net forces that we've seen in previous units where we sum all those forces together, and this is our unbalanced force. So net work is just net force times delta x times the cosine of theta. Just a quick reminder that theta is the angle between the direction of motion and the direction of the force. So if I've got my force being applied to the left and my object is moving, I'm sorry, that's to the right, force to the right and the object is moving to the right, that is a angle of 0. And if I have a force to the, a direction to the right, but my force is to the left, that is 180 degrees. Biggest example where we'll have 180 degrees is if we're talking about friction. Remember, the force of friction always is applied in the opposite direction of motion. So friction a lot of times will be 180 for that angle. Moving a little bit forward, and we'll come back to those and tie them to some other concepts in this next slide. But we've got our three sort of types of energy that we talked about: kinetic energy, potential or gravitational potential energy, as well as spring potential energy. And when we add all of these together, if we added those three things together, we get our total mechanical energy, what I've been representing as a capital E. That can be, sort of represented in words as mechanical energy or total mechanical energy, or sometimes, I don't know if it does on the test. Let me just take a quick look here through it. I think most of the times the test will say either mechanical energy or total energy, not necessarily just energy in general. So if we add all three of those things together, that is what we call our total mechanical energy, or capital E. So kinetic energy is 1/2 mv squared. Anytime you have motion, you have kinetic energy. Kinetic literally means motion. So if our object is moving, it has some kinetic energy. for gravitational potential, as long as our object is off of the surface of some gravitational body, then we have gravitational potential energy. And that's important. If there was, an object by itself cannot have any gravitational potential energy. There has to be what's called a mass Earth system. Mass Earth system in order to have gravitational potential energy. Without that force of gravity that the Earth is causing, there's no gravitational potential energy. For instance, if that mass was just floating out in space all by its lonesome, there's no gravitational potential energy because there is no acceleration due to gravity, that lowercase g that we've seen. And last, if we have a spring, then we have some spring potential energy if our object is attached to a spring. So then that is represented as 1/2 kx squared. So those three things again together make up our total energy when we add them together. And we'll see here in a little bit how to work with some of those. So moving on, we also do have power, and that's sort of the next step with these. Let me move that out of the way a little bit. And power is work over time, or it is change in energy over time, or it is P power equals FV cosine theta. So for this work over time, we can also substitute in this equation. So we could have power equals F delta x cosine theta over time. Remember that time does have to be in seconds, our standard SI unit. But work and change in energy, again, we'll see those down on the next slide. But those two things are kind of the same thing. When we have a work by a non-conservative force, one that would generate some power, that is a change in total mechanical energy or mechanical energy. So those two equations are the exact same thing. When do you use one versus the other? Well, if it's talking to you about a force and distance, I might go ahead and use F delta x cosine theta over time. But if it's talking about a change in speed or a change in height, then I've got it easier to calculate maybe a change in energy if I'm speeding up, if I'm accelerating, or if I'm increasing my height. Then I could use that change in energy over time. Or if it gives me a force and a velocity, some of the problems we'd seen before says that you have maybe a person in an elevator, and the elevator is going up at a constant velocity. Let's call it v, and it tells you the mass. I'm sorry, not the mass, but the weight of the person. So let's say this is a 900 Newton individual, and it says it's going up at a constant velocity. So these, I think there were at least two of these types of problems on the review practice problems, the test practice problems, where it gave you the mass and then wanted to know about the power generated by the upward force. So if the person weighs 900 newtons and we want to know what this force is, but we know it's moving at a constant velocity, these forces have to balance each other. They balance to move at constant velocity. Because if they balance, that means we have a net force of 0, and net force of 0 means 0 acceleration, and a 0 acceleration means constant velocity. So those were represented a couple times. That might be a good thing to make yourself familiar with. If things show up multiple times, we've talked about it a couple times, they tend to be represented, at least in some way, on some sort of assessment. Let me clear up a little bit of this here. And the last thing we have on this slide is our spring force equation. The force of a spring, the force that a spring applies to an object hanging by it, is negative k times x. Remember that k is our spring constant, and the x is the distance that the object has been displaced from its equilibrium position. So let's say we had a spring that was hanging here, right there. And when that is hanging, that is where it stops. It comes to rest at that place. So then if I stretch that spring, if I pull down on my object, the difference in distance from here to here, those two centers of mass, this distance here is my x. It's not about the length of the spring. It's not about how much closer to the ground it might be. It's about how far that spring got stretched is your x there. The negative is just about direction, and the force of a spring always pulls so that the mass tries to get back to this equilibrium position. So it's not always down or not always up. It's not like gravity, where gravity always points down. In this case, it's always in the opposite direction of x. So if I make x positive when I pull it down, my spring force is negative, and it pulls back upward. All right, putting some of these things together a little bit. The first way we want to do that is with our work energy theorem. If we have a net work that has been done, that is a change in kinetic energy final minus initial. So we can connect some of the stuff we saw up here, this net work equation, net force delta x cosine theta, that is equal to a change in kinetic energy. So it would be 1/2 mv squared final minus 1/2 mv squared initial. Next up, we have work done by non-conservative forces. Whenever we have a work that is being done by anything other than a spring or by gravity, because those are our two conservative forces, when we have other work, such as someone is running to accelerate themselves, or we have an engine or friction, in those cases we actually have a change in total energy, in total mechanical energy. So that is our energy final minus energy initial, which gets broken down to be equal to this plus this plus this. All those things go together to equal total energy. So in this case, if we broke this equation sort of all the way down to its most basic units, we would have a work done by a non-conservative force is 1/2 mv squared, and that is our final velocity, plus mgh final, plus 1/2 kx squared final, and all of those are together. And then we would subtract the exact same thing, but for our initial energies, 1/2 mv squared initial plus mgh initial plus 1/2 kx initial squared. And another big question I've heard is, well, how do I know which ones I have to include? Because there have been a lot of situations where either we don't have a spring or we don't use the kinetic energy or whatever. So the biggest thing is to ask yourself three things. Number one, does my velocity change? If your velocity is constant, then whatever velocity you had to plug in there is going to get canceled out. Whatever number you had here, it's going to be the same, and then it's going to get subtracted by itself. So those will cancel out. And if the same is true for your height, if your height doesn't change, the same thing will happen. If you do not change heights at all, you don't need to take mgh into account there. It won't do anything, no matter what height you pick. And last but not least, if you don't have a spring, don't use the spring force. That is, without any spring, you're not going to have any spring potential energy. So in that case, you would then ignore those. Let's see what I can do here. Erase a little bit of this. It's not going to let me erase that top part, but that's okay. Next up, if we didn't have any work done by a non-conservative force, so this would be a situation where we did not have anything other than gravity and spring. Remember, non-conservative, let me get my thing here. Non-conservative equals anything except for gravity and spring. So if those things other than gravity and spring are zero, that means we only have gravity or springs, and then we set those two equal to each other, our final total energy is equal to our initial total energy. And again, same thing here. If you don't have any change in movement, both of these will any change in speed, both of these will cancel out. If you don't have any change in height, both of those will cancel out. And if you don't have a spring, don't use spring. And again, from up above, we did see this equation, but it's popping up here again one more time. This slide, do not worry about. It won't be on the test, and it's likely to not show up on the AP test either. This is a very general equation for gravitational potential energy, so it doesn't really show up ever, and we're not going to worry about it. Down here at the bottom, I am realizing that there is a little something, and again, it's not going to let me erase this. Let me see if I can back these out. There we go. These two things, the work done by gravity and the work done by spring force, notice that they are very, very similar to their potential energy equations. The work done by a conservative force is equal to the negative of its change in potential energy. So when we get into some of the graphs, we will see why that sort of matters and how that can help us out down here in a little bit. Speaking of, we got some graphs. So the first ones we saw were force displacement graphs. So this would be F versus delta X or versus D. So two things here. Number one, the area underneath that curve, the integral, is the work done. So if you get that area, then you can say that work is force times distance times cosine of theta, connecting that back to that equation. Or if this force is non-conservative, then this work, that integral, is the same as a change in total energy. Because we said a work by a non-conservative force is a change in total energy. We also have net force. If we sort of took our net force and graphed it against the displacement that it occurs across, then we can get the net work, which we said up above was change in kinetic energy, the work energy theorem. A net work is a change in kinetic energy, just speed there. So if a problem asks you about a change in just kinetic energy, consider trying to find how much work was done. And that's much easier than trying to make all of those calculations out with the energies. Scrolling on. We also have a force displacement graph for the spring, or for any spring that we have. Remember, the slope of one of these is the spring constant. It's newtons per meter. Well, that is rise over run. That unit kind of helps guide your thinking, hopefully. And again, if we have a force displacement graph, that is work. And for a spring, that is the work to stretch that spring. And from that little blurb up above, that is also our spring potential energy. The more work I put into that spring, the more energy I get back from it. When I stretch that spring, I am doing non-conservative work. I am, my hand is not that spring, so I am actually gaining total energy when that happens. Last couple of graphs we saw, we have energy now. Instead of force, we have energy. Be careful on these on these graphs. It is easy to get in the mindset of either force or energy and pick the wrong one to think about it. Like on an energy distance graph or an energy displacement graph, the integral is not the work anymore. It is something completely different. So this time, instead, we just use these to sort of look at what is happening with our objects. So in this example, we have falling with no initial velocity and with some initial velocity. Again, these showed up many times in the practice problems. I would get familiar with them. It certainly wouldn't hurt. So here, if we are just falling, that means that gravity is the only force acting on it. So we have a work by non-conservative forces equals 0, which means that our change in total energy also equals 0 because these things are equal to each other. So that's why we have this flat top line. Because we don't have any change in total energy, no matter how far we fall, our total energy has to remain the exact same. So as we fall, we end up losing potential energy. As we get closer to the Earth, that MGH equation, we get less and less and less height. So as we fall different distances, we lose that potential energy. And at the same time, we end up gaining kinetic energy. Whenever we lose potential energy, we gain kinetic energy. It's a trade-off. That's where we're conserving that total energy. We're keeping the same line by getting rid of some of the potential energy in exchange for some kinetic energy. The only difference with this graph is that we started with some initial velocity. So let's say that instead of just being dropped, instead of dropping a ball, we threw it off of a rooftop. So we start with an initial kinetic energy. Again, we start with the same level of potential energy. Hopefully it should be about parallel. But this time our total energy is higher, so that graph just kind of got shifted up a little bit. Last point I want to make here, this point of intersection when we just drop an object is where we have half kinetic energy and we have half potential. That is halfway down. When we are just falling, halfway down is where we have lost half of our potential energy and gained half of our total kinetic energy. It is not necessarily half the time that it would take to get there, but at half the distance fallen, we have lost half of our potential energy and gained that same amount in kinetic energy. In fact, at that point, our potential energy, that should be a G, I'm sorry, is equal to our kinetic energy at halfway down. At that intersect. That is true if we drop it. It's a little different when we have when we've thrown an object off. Again, the intersect is where those energies are equal, but as you can see, it is not halfway down this time. Last couple types of graphs that we had. This time, energy versus time. So this one, to sort of help try to get it in your brain why it's curved this time instead of being those straight lines. As we drop an object, it speeds up. So as it speeds up in the same amount of time, it falls a farther distance. And I think a couple days ago, probably I showed you guys how you get a square on that t if you substitute in to get t somehow equal to energy with a bunch of other variables. But it is a squared function. So it is a quadratic, so we will end up with these nice curves, and we treat them the same way. It is at this time that our kinetic energy and potential energy are equal. So it's actually at this time, way later on, that we are halfway down. We get halfway down, it looks to be about 3/4 of the way. I'm not sure what the exact calculation comes out to be for that. But when those intersect, our kinetic energy and potential energy are the same. Again, our total energy remains the same because we're only working with gravity. It is a conservative force. We don't gain any total mechanical energy there. And again, here you can see that because we threw it with some initial velocity, that kinetic energy line is just shifted up a little bit. And the spring the spring graph. So again, this is quadratic because we have that if we've got energy equals 1/2 kx squared. If we're graphing energy versus displacement from that equilibrium position, we've got this nice square on it, which gives us a nice quadratic shape. So at the equilibrium position, I'm going to try to zoom in here a little bit on this guy. Let's see. Here we go. There it is. So if we zoom in here at the equilibrium position, where it's sort of at rest, at its resting position, Then we have a potential energy of 0. We did not gain any. Our x is 0, so our potential energy is 0. But as we stretch in either direction, we continually gain more and more and more and more potential energy. The farther we stretch it, the more work we have to do to stretch the same amount. So we see sort of an increasing gain of potential energy for that same distance. And again, just like the last one, our kinetic plus our potential has to add up to be our total energy. And again, with a spring, that is a conservative force, so we keep the same total energy up there at the top, and these are inverses of each other. So at the 0 position, we have all kinetic and no potential, and at the farthest out positions, we have all potential and no kinetic. All right, so now comes the point where I'm going to take a look at the test and sort of just hit anything I might have missed in that previous sort of setup. I know I'm just briefly looking through it now, sort of scanning over it. A lot of it, excuse me, has already been covered. A lot of that that we just did is going to take care of most of the test, but there's a couple highlights I want to hit, a couple things that you would want to focus on. And the first thing is graphs. Graphs. They are all over this test, both in the multiple choice and in the free response. Knowledge of every type that was up above. So if you are having troubles with that, make sure you go back into those graphs and really get comfortable saying, all right, whether it's the different types, how does an energy versus position graph look, or an energy versus time graph look, or the spring graphs look? Are they quadratic? Are they straight lines? Are they flat lines for total mechanical energy, as long as we're not losing any? Just kind of skimming through here. Oh, here we go. Just a quick reminder for kinetic energy, potential energy due to gravity, and potential energy for spring. One of the things that gets hit is, let's say that this happens, something happens. How does that affect each type of energy? And we'll put total mechanical as well here. So for kinetic energy, if we increase our velocity, our kinetic energy increases. And vice versa. If we decrease our velocity, our kinetic energy decreases. For gravitational potential, if our height increases, if we increase our height, then our potential gravitational increases. And if our height decreases, then our potential gravitational also decreases. For springs, if the distance away from the equilibrium position increases, then our spring potential increases. But if we go back to equilibrium, put EQ there, if we go back to that equilibrium, then our spring potential decreases. So with this X, it's not whether it gets, pulled down or compressed, expanded or compressed. If either of those things happen, so that the object, whatever's hanging by that spring, goes away from that equilibrium, then our spring potential energy increases. And for total energy, let me sort of pull it down here a little bit if I can. It's not going to let me, but that's okay. I'll just shift it over this way. So for our E, for our total energy, if we have no work done by a non-conservative force, if only gravity and or a spring force is acting, then this stays the same. But we can change it. If we have, some friction, this is going to decrease. Friction, that goes down. But sort of the other more general way to look at it is to look at these other forces. If kinetic energy and potential energy both go up, so if I'm increasing my kinetic energy and I'm increasing my gravitational potential, that means my total energy must go up. That goes back to that first equation where we added all three of these together to equal total energy. If they all go up, or all the ones that we're dealing with go up, then our total energy has to go up. If they all go down, total energy has to go down. Let's see, what else do we have? Talked about that. Talked about that. Talked about that. Oh, let's see. I'm going to switch to another slide. So, sort of back to work. Sort of in general. The direction of work, or the, not really direction, it's a scalar. But if we do positive work, that means we are speeding up or increasing energy. And if we do negative work, we decrease energy. So this kind of goes into that angle of, in that cosine of the angle, that angle there. If that angle is, we'll call it less than 90, then you'll have positive work. If that angle is less than 90, you have to have positive work. The closer it gets to 90, the less work is actually being done. And then once you get into the sort of 90 to 180 range, that means that your object is being, let's say that it's moving this way, this is its direction of motion, but once you get past this sort of 90 point, that means that you are applying a force in the opposite direction. That means you are decreasing the energy, whether you're slowing it down or if it's losing potential energy without gaining kinetic energy. Whatever, you are taking away energy from it if it's in that opposite direction. And if we had maybe a force that was being applied at that 90-degree angle, that is not doing anything to its energy. The only thing it's doing is changing its direction, or at least trying to. Whenever we have angled forces, at least some of that is being used to change the direction of our object. So if I'm, think about it, if you're running to the right and someone pushes you sort of upward, so let's say I was, this is me, and I'm running this way, and someone pushes me from this direction, I'm going to turn a little bit. They're not doing anything to increase my speed or decrease my speed. If they push me at that 90-degree angle, they're only turning me. This goes back actually a little bit to our centripetal motion unit, our uniform circular motion, when we had that force was being applied to the center, but our velocity was at a tangent. All we were doing was changing direction there. And then we're looking at a lot more graphs. I will say this, that every single problem in the free response at some point was represented almost identically in either a homework problem or in a one of the test practice problems. There are no surprises in the free response section. They are all questions that have been seen at least once, if not 2 or 3 times. Biggest thing, guys, just don't get overwhelmed. I have all of the faith in the world that you guys know how to do this stuff. And remember, whatever information it gives you, use it in some way, shape, or form. If it gives you forces, use some equation that involves force. If it gives you speeds or it gives you heights, maybe consider using one of the energy equations as opposed to a force equation. It's a lot easier to use equations where you have some of the variables already, as opposed to trying to derive brand new equations. So look for equations on that green sheet. I know they're not represented in the best way possible, but look for ones that involve what you have. Don't go trying to reinvent the wheel. A lot of the times, it's a simple matter of picking out which equation is going to work for you. Thank you all for listening and tuning in. I hope this was helpful. And good luck this week on our test. Have a good one.